So before we get started with our keynote speaker, I just want to announce a couple of things and make sure everybody's remembering what the schedule of the day looks like. So here we are at lunch in the middle of the page here. We're moving into our keynote speaker. Then we're going to have a coffee break. During the coffee break, there's a wall that's going to be put in to separate that room from the rest of the grand ballroom. Immediately after that, we'll have the autonomous systems invited speaker session on this side, and we'll have the socioeconomic issues invited speaker session on that side. And so you can choose which you want. Each has 4 speakers, invited speakers, roughly 25 minutes talks each. And then we'll put the wall back. We're going to have, we got about a 20-minute break in there. We don't have anything specified there, but about a 20-minute break. We'll move the wall back. We'll open this back up, and then we're going to have an invited expert panel of growers, farmers from Mississippi, Alabama, and Illinois. And then I just wanted to remind everybody about the dinner and social this evening that's going to be at the football stadium at the Gridiron Club. You do not want to miss that. It's going to be a lot of fun. We're going to have buses that are going to be lined up out here to take people from here to the football stadium, and then they will bring you back later. The buses will be out there starting at 5:30, immediately when the grower panel ends. So please, just when you get done here, jump on the bus, go to the stadium, and we'll enjoy the festivities, dinner, music, everything that we have going on there. So without further ado, I would like to go ahead and introduce our keynote speaker. John, are you here? I saw him just a minute ago. There you are. Sorry. I thought maybe you'd stepped out for a moment. So our next keynote speaker is Dr. John Reid. John is Executive Director for the Center for Digital Agriculture at the University of Illinois, Urbana-Champaign. And John, I'm going to let you complete the detailed introduction if you don't mind. But without further ado, John Reid.
Thank you. Does that work? Great. Thank you, everyone. It's my pleasure to be here. As Alex said, I'm the Executive Director of the Center for Digital Agriculture at the University of Illinois. I've been in this role for about 2 years now. Prior to that, I was at Illinois as a faculty member, tenure-track faculty member from about 86 till 2000. And then I took a 19 or 22-year sabbatical leave. 19 of those years were with John Deere, and where I was the Director of Product Technology and Innovation during the Precision Ag explosion. And then I worked in recreational marine for a couple of years before returning to academia. And so I'm going to talk today about some of my experiences in automation to autonomy and thinking about engineering the next generation of agricultural systems. And before I say that, in my role at the university, I've also been able to, I was telling somebody at lunch that I'm building my research lab again, it doesn't look like I'm very early in my career, right? But I'm at the beginning, and my team works on embodied AI in agriculture, Gen AI, intelligent agents, visual grounding, and autonomy. And so let's talk about the journey in precision agriculture. It's all a journey about moving from automation, which started in the 90s, towards autonomy. And here's a couple of curves that represent that. I borrow this from Ian Morrison, who wrote a book called The Second Curve, and everybody's kind of on a predominant curve and thinks the world is going a certain way. But there's an alternative curve that's emerging, and sometimes they work together well, and sometimes it's a jumping off point. And my point here is that if you look at the black curve, where we went through machine guidance and self-adjusting machines and things like mission planning, coordinated machines, all a really part of precision agriculture, that's been a heavily influence on the journey to autonomy. In fact, if we take precision agriculture to its logical conclusion, we will see that it results in optimized human-machine solutions, humans in the loop, operators of the machines, working with farmers. And today we're kind of at a point of AI-enabled decision-making on these machines. And at the same time, a second curve kind of emerged with the explosion of digital technologies in society, really, but impacting agriculture. And things like cloud computing and mobile devices led this opportunity for IoT and sensor-enabled management. And actually, I think from a worksite perspective, we're kind of in an interesting intersection. We're starting, I'll talk about job steps later today, but when you're in a farming production system, you have jobs to be done, and you have different parts of the production cycle, whether it's preparing the land or planting or protecting the crop or harvesting, and then repeating over and over again. And I will kind of have a point that I believe that we're on a journey towards more of an optimization at the farm scale or worksite scale, and maybe out into the value chains and supply chains that are connected to farmers. And AI is an emerging technology we have today, and we've talked a lot about it in this conference, and so I'll be mixing automation and autonomy and AI and talk about each of them. But AI is going to have incredible value in the journey from automation to autonomy, and as we know, AI is a broad field with lots of different pieces. So another way of looking at automation and autonomy is compare the benefits of automation and the case for autonomy into the future. Autonomy isn't just a cool tech goal, it's a necessity, and we have challenges with labor availability and limited skill and continuous use of that skill over long periods of work periods. And we have environmental pressures and these types of things. And so agriculture is kind of a complex, time-sensitive system. And we would like to make it more productive and more efficient by kind of managing that complexity. Precision agriculture has provided a lot of these benefits. Actually, I should have put a video in here from 1987. I was my PhD work at Texas A&M was an automatic guidance of a tractor with computer vision, and so it took like till 2016 till John Deere took that into a product. But nonetheless, yeah, sometimes there's a long tail between coming up with an idea and showing the technical feasibility and making it work. I always thought about how vision would be related to reducing operator fatigue, and it is a big part of this. But you know, by 2000, we started realizing it was so much more than that. It was increasing the job consistency and accuracy. The idea of being able to operate at night, which I'm sure farmers in the room don't want to do that, but if a storm's coming, it's kind of nice to have the capability to do these types of operations. And some places do 24/7 operations. Improving yield through higher density planting and precision. Increasing the productivity of the machine as well, while being less dependent on the skill level of the operator. So I had one farmer tell me one time that this AutoTrack system was working so well, he would even let his dad plant. And so, you know, that's the kind of thing where, and I know that would be true with me because maybe I wouldn't be able to keep the attentive span. But really a big part of it on the left side is data collection for decision making. It was kind of a beginning of that era. Now, as we talk about autonomy, we also think about its labor abilities, whether it's labor replacement or augmentation in critical roles. Again, we can do things like day-night operations. But I think we're really kind of thinking about getting broader benefits of consistent task execution under wider ranges of environmental conditions. And I may use the word tractoring a little bit, but today we're almost in a mode of always thinking of autonomy and tractors together because of the utility of these vehicles. But we really need to think about an integrated system that's creating a job outcome. I'll come back to this. And autonomy is going to allow us to move from productive machines to thinking about the work site itself and how do we optimize the performance of machine systems across those work sites. And in order to do that really well, we're going to need to get the quality of the job as part of this. It's not just dragging iron across the field precisely, but it's making sure that we're making the right decisions at every point in the field to maximize the productivity, plant the seed at the proper depth, and all those types of things. There's also a really important piece to this. There's data on the right side as well. And without integration, with cloud, farm management information systems, and the ability to ingest this data. Autonomy is not going to be too interesting for agriculture. We're not really, farmers don't farm with Roombas, and they don't just let random cleaning or mowing of the grass and things like that. Those things can be done, but it's kind of structured and precise, and it's going to be really important that we leverage that data in FMIS to make these things happen. So here's kind of a picture of the modern ag operating system from a one-color perspective, green and yellow, okay, two colors. It requires high-fidelity location of equipment. Wow, I didn't realize that white was going to be so bright on the screen. But connectivity and telematics, we have cloud-based services. And actually, electrification is really an important part of this, not so much for its ability to, it's helping the machine system deliver the autonomy through optimization of the powertrain and having implements with very controllable functions. But the most important thing on this chart is the FMIS. And it's the way that we run and manage these systems and to make it work effectively. You'll see on some slides I have references. This is actually one that John Deere, Mark Moran, formerly of John Deere, and I gave to the National Academies a few years ago. Now, okay, back to this thing of jobs to be done. Autonomous agriculture is not just executing the task, what's in orange in the screen. It has to handle all of the workflows. And when a farmer is doing a job, they just don't think about the time they're driving in the field doing the operation. And most of the time they're having logistics and things to manage besides that. But one of the things that's kind of a flaw in today is that we like to show the execution of the job. But really to make these systems usable for farmers, we have to think about all of the job steps and understanding what the job is, defining it, locating all the stuff that's needed to get it done, and by the way, getting that stuff to the right field, preparing, setting up the environment to do the job, and understanding where all the conditions are ready. Is the field too wet and able to move ahead? And then there's the actual execution of that task. And while they're doing that task, it isn't like they just are, I'm not really a big fan of the idea that a farmer steps out of a vehicle and hits a button and it goes autonomously, because you need to know, well, I did see one farmer in the room monitoring how their systems are working yesterday during a meeting, but they have to monitor that stuff and know that things are happening, and maybe you need really precision monitoring. And then there's modifying and making changes based on what you encounter. And then after all of that is over, if you've been successful, you have to clean it all up, put it away, and all of that. And one of the things that we have to get beyond is just this thing of thinking about that one part of the process. It's a hard one, and it's the fun one maybe, but it's also really important to think about these others to make that work. So a little bit about AI in agriculture today. It's already in a lot of places, and we've been spending a little bit of time discussing Gen AI. But if you look at the examples that's in product, if you have systems that are already, AI is improving machine performance, whether it's vision-based guidance on computer vision machine learning, or on the right side you see a path plan. These are areas, the black areas are keep-out areas in the field, and in the other areas is an optimized way of traveling through that field at the minimum distance and deciding that through computer control so that you basically can gain that efficiency. We see AI augmenting human performance, and the best example of that is in the lower right corner, where you see the example of a combine, or actually an SPFH, could be a combine, unloading into a wagon. And with this type of machine, the corn is so tall you don't even see the tractor driver on the wagon. So how do we take the stress out of that so that we can make this work together? And part of it is just GPS and a nice control algorithm, keeping the machines synchronized. But the AI part is understanding how full that wagon is through stereo vision, estimating the volume, and nudging the tractor wagon system forward and backward to make that happen. Multiplying human performance is an opportunity for autonomy. Is an example shown here with the autonomous tractor. And the idea is that if I'm going to multiply performance, I'm going to be able to do something else as a farmer while this one other tractor does something with me. And there's various ways of achieving that, but the one that's currently popular is to talk about autonomous tillage and expanding it to other operations. And then there's this part, I call it exceeding human performance. And the reason it's exceeding is it's related to the spot spraying we've talked a lot about. It isn't that humans can't spot spray really effectively. They can actually spot spray better than this by walking through the field with a sprayer in their hand and doing that very precisely. But talk about doing it at 12 miles an hour and doing it across a 110-foot boom. That's where it's an interesting area to think about, where AI can help achieve this. And I think this is one area that we need. I'll come up with this later today, but we need to talk a little bit more about making the implement intelligent and automated on the journey towards thinking about the rest of the system being driverless and autonomous. Okay, so let's also dive into a few of these examples. Machine perception is just really important to have autonomous systems, and perception's only begun to be integrated into agriculture. In fact, agriculture for a long period of time, there's almost a bias against, well, we don't want any cameras helping us see those hidden areas because now you're talking about safety. But safety and autonomy have to go together, and as you heard earlier this morning with Andrew talking. But before that, we actually had some task-oriented opportunities that were applied, like vision guidance. It's not an incredibly safe system. It's not detecting obstacles. It's just detecting where you drive, and so it's kind of a discrete function that can be delivered through autonomy, or the active fuel control that I showed for the wagon. In this case, it's using stereo vision, which gives you volume estimates, and it's not doing anything except telling you how full that wagon is and giving you a discrete output. That's great. It helps us get towards autonomy, but on the right side is the bigger deal, is situational awareness, because this is replacing the most important part of the tractor, and that's the driver, the operator that's doing this work. Situational awareness is understanding what's around the vehicle and not running over anything you shouldn't. And it's also understanding what's happening on the implement and understanding that you're protecting the footprint of that machine, and is very critical. And we're just now starting to see these types of systems be used for this purpose. And it really is part and parcel to some of the talk this morning about functional safety in agriculture. Okay, so let's look at an example to kind of take a break from this. So about 2009 or 2011 timeframe, something like that, I had the opportunity to be part of an industry member on a USDA-funded project on autonomy. Actually, Carnegie Mellon received 2 of these projects, and they were very different, but both very insightful. One was around working with a specialty crop customer, and this was part of U.S. Sugar in Florida, and they already had a highly automated work site. And their goal was to basically, the work site was automated inside the factory, the orange juice factory. Their goal was, why can't we do that outside the factory and deal with the challenges? Because they had lots of labor across a wide geographic area around the factory, and they wanted to basically have asset optimization for the field operations through autonomy. And they looked at it as a way of increasing the productivity of their work site. And so we devised a system that's kind of illustrated in the picture that allowed one person to manage the operation of 3 to 5 tractors. Each tractor was either doing a mowing or spraying operation, so the actual operation was fairly simple. And the concept behind this is that you have infrastructure and data and a farm management information system that allows you to manage this remotely, away from the dangerous chemicals. In a controlled environment, could be a truck, but also we had a version of this as within kind of like a security guard station. So in previous jobs, we talked about upskilling today, the previous jobs were to drive the tractor and to do all the tasks. In this new concept, the operator is more like a monitor of multiple systems and managing the complexity of those systems. And so it's an upskilling and required actually hiring a different kind of employee for this task. So the solution concept we came up with was multiple autonomous vehicles managed by a remote supervisor and pulling operators off of individual machines. Now, we were able to get some benefits of autonomy by applying AI, and one of them was to take, on the left side, taking orchard blocks, which are fairly complex. There's lots of areas you can't drive, and there's, have to turn around because there's infrastructure that you have to avoid. And actually, both of these are AI-generated plans, but where you see the black lines are places where that you had to pass through that road twice in order to cover the field. So that's inefficient. You're going to have to make some passes through in order just to get to the next pass. With AI, we could reduce some of that, but you can't eliminate it. But I can tell you it was much better than the human operators. If they were mowing, they could tell where they were at. And maybe they could tell where they're spraying, but if the leaves dry out a little bit, then it was kind of hard for them to know, did I actually pass down that row? It's very confusing and complex because everything looks the same. On the right side was also some benefits that we could see from being able to, we had to do things like detect trees and travel through them, and trees grow big and bushy with new branches, and not all limbs are obstacles, and you have to detect that and manage it. And that creates challenge for planning, but essentially we were able to successfully use perception systems to navigate through the rows. And I'll talk about this later, but we're able to travel at 25% faster than the operators could travel. So here's a little video of this. We actually gave this system, it's really important to have humans in the process and not PhD students doing the work. We had this in the hands of the customers and the operators for over an 18-month trial. They basically hated us when we pulled it out, which was a common pattern that we did because it wasn't a product yet. But they successfully used it over a long period of time. And to give you, I'll just show you, we kind of staged this so you could see two vehicles making a turn. The first one, you can see all this stuff on this tractor. Remember, in 2009, what was the state of infrastructure around communications? If you wanted to communicate and have images and videos, I know all of you probably don't realize, but as 15 years ago, we couldn't actually do a live FaceTime everywhere. So we had to build infrastructure, put up towers to have that kind of communication. By the way, if you can do that, it makes autonomy really much easier. Today, the infrastructure is in society. And the second vehicle was a mower that's basically just going through, and they keep the grass mowed and kind of clean up. So we did that kind of operation. So here's the data, though, that shows some of the benefits that we get out of the productivity improvements with limited autonomy. This system was not perfect. It had a lot of false positives. The human operator had to deal with 5 or 6 incidents an hour where the tractors would stop because they were conservatively programmed and didn't have all the sensors that maybe we'd like to have. But even stopping and having to restart by monitoring the system, they ended up being 30% more productive than their other workers that are driving machines at the same time. And so one of the benefits, what made that possible, I showed the path planning, resulted in shorter paths due to optimization through the planner. And the autonomous vehicles, actually, it's really interesting. As you can look at this upper graph, they're able to spend, you have this kind of bins of times at different speeds. But the autonomous vehicles spent more time at higher speeds. And I rode in some of the vehicles to see what this was like, and part of it was I was afraid to drive that fast through the orchard. But it wasn't unsafe. It was just with trees on both sides, I was reluctant. Well, the autonomous system had no emotion. It was able to do that very easily. And so in some ways it's a cheat because we can program it to be more productive right out of the box, and that's what we did. And so in this productivity improvement is meaningful. 30% productivity improvement is something the customer cared about. And by the way, it didn't take away any jobs because they had a lot of these types of activities. We didn't, in this case, upskilling. It wasn't just basically training the tractor driver to do this. The tractor driver didn't want to do this job. He wanted to drive tractors and do other kinds of work on the farm, and so they actually created a position, hired a person that was in this skill level. So you can imagine that part of our upskilling is thinking about training new workforce. Okay, so how am I doing on time? I'm still good, I think. And I'm going to start switching a little bit. I want to leave some time for question and answer, but I'm going to go into this idea of designing autonomous solutions because we have a kind of an industry academia and some groups that are in startups. And for 14 years, I ran an innovation function at John Deere, and I got a lot of insights and learning. In fact, I have a saying in life that good judgment comes from experience. Experience comes from bad judgment. I've had a lot of experience, so I'm trying to share some of that with you. One of the areas that isn't very difficult to see is that innovation begins with understanding the problem. If you want to catch me in the hallway and talk about how you bake a cake, innovation is like creating a cake of a certain kind of innovative cake. The ingredients are the things, the technologies that make that possible. And unfortunately, we usually have people who only want to do robotics or only want to do whatever they're doing. And these kind of problems are the integration of ingredients together to provide a solution. The number one thing is you have to have a deep understanding of the challenges and the pain points. And I know the universities talk about use-inspired research, but I bet you in this room, if we could do a survey, we all have kind of a very narrow, specific view of what a farmer is and does, and don't realize that there's a diversity of farmer practices and labor that works with farmers that achieve the job. We need to understand their economics and understanding the jobs that we're trying to do. And then if you have that, you don't typically, I mean, if you're really lucky, maybe you can, like this grain weevil thing I think is totally awesome. It solves a problem, it's very specific. It actually even has adjacencies to grow into other markets that could use this that are not grain related. But many times, in autonomy and robotics are this area, you need a combination of technologies to make this work. Remember I mentioned digital connectivity. All of these types of things are really enablers for this. And so we have to think, though, what's the value proposition of these ingredients working together? And quite frankly, for my career in industry, it's only three things. Does it improve productivity? Does it address uptime issues, minimize downtime, in other words, and does it lower cost of operations? And if you have that, you can have different types of measures, but you can make decisions on innovation opportunities based on these. And then finally, you have to deliver value. And unfortunately, this is the cost side of the equation and the dollar signs. And engineers need to get comfortable with talking about the dollar signs in the R&D phase, because they don't pan out to be exactly the same in the future. But if you don't do the math and understand it, it's hard to vet ideas. And you have to provide value for the farmer and producer. And at the same time, if you're creating a company, you have to create significant value to keep you in business as a company. Okay, so kind of some other elements of this. In my days in recreational marine, I got really comfortable with a different way of doing this. It was called human-centered design. There you have your users, or the humans that are on the boat, but you can think about a farmer is the user. And what your solution has to be desirable for them. And understand if it's desirable, you have to have empathy for the end user and understand their attitudes and desires, customers, pain points, that kind of thing. And then there's the stuff that people in the room are probably really good about with feasibility. That's technical. Is the technology readiness there? Is it going to be able to be supported and deliver the solution effectively? And you can't take shortcuts through some of those. And then finally, there's viability, which is the business side. And you have to be able to have that return on investment. And the innovation is where you have the sweet spot at this. Actually, in industry, I had teams that wanted to join our innovation team, and we had trouble because we found out that they were frustrated that we wouldn't let them do anything in the world they wanted to do. And so finally, we did this exercise where we created a box, and we just brainstormed on ideas, and the idea was to put the sticker in the box if it's innovative, and a sticker outside the box if it isn't. And it surprised me to learn that most people believed that if you tried to do something that could be successful in a large company, it wasn't innovative, because we weren't free to just do whatever we want. But you have to make money at these things, and as a result, we had to do a lot of work convincing people that you can do innovation, at the same time do things that are good for the customer, for the business, and still enjoy the pleasure of technology. Okay, so developing autonomous solutions. I know jobs to be done, and you're going to develop an autonomous solution. You've got a use case. I want to do autonomous orchard spraying. And starting with the jobs to be done, it requires then more than focusing on the task execution, as I've said. We have to understand all of the steps, and we have to map them out. We have to understand the processes required across the entire production activity, and we have to rethink what can be done so that our technologies can be used to execute this. One of the things I learned over time is to bring in people that are experienced in essentially ethnographic research, human factors, you can maybe think of it, but it's actually, I defined it as user experience. And basically you have to kind of take the customer, their problem, know how they do work, and on the right side you see an example of that for a customer that was very interested in autonomous orchard spraying. In fact, they were so interested, they said, if you can do autonomous orchard spraying, we will switch to autonomy. Hold that thought for a second. And so we looked at a typical operation, and it included a block of trees. There was a supervisor that was the supervisor over the workers. There were 5 tractors, 5 tractor drivers. There was a station to refill spray, and there's a truck that came around to refuel fuel. Great. Let's make this thing autonomous. And we started looking at ways of doing this, and it's like, well, one of the things was clear is you're going to replace 5 drivers, right? Unfortunately, what was also not clear is the 5 drivers could tell if there was a wet spot or if a tree fell down overnight, and the 5 drivers could also refill their spray tanks by themselves. So it turns out that instead of removing 5 people from the operation, we could only remove 4 because we had to put somebody at the station to fill the sprayers as they came around for refilling. You could have made that autonomous, yes, but we made a trade-off that wasn't worth doing at that time. And then the person who was a supervisor talking to people, their role became the mission manager and running the operation. And so that's kind of a representation of this. By the way, it worked slam dunk, excellent, and so you're probably wondering why you don't see a lot of these tractors out in the field, because the goal was to replace labor. As soon as we successfully completed the project, the farmer we were working with said, so what about the other operations? About pruning, picking. And he had the realization at some point that there's not going to be any labor savings in spraying until you can do it all. And I think that's going to be an issue for autonomy. How do we find a way to incrementally get there? Because we can't wait for the whole farming system to be autonomous. There's a transition, as some of the speakers talked about this morning. Okay, so here's a couple of examples of implementing the human centered design process in R&D. That might seem unusual to people, but it's really important that this doesn't start at the product design phase, but you start doing upfront research, understanding the users, and doing the analysis, building empathy, determining the right levels of automation, and then start concepting systems. I've used this approach in mowing stadiums. We've used it in autonomous utility vehicles for the military. And we've used it in this orchard management project. And it's incredible, the learnings you get in R&D, because you talk to people and you get their idea, but until they're using the technology, they're not telling you the truth. They're only telling you what they think, and sometimes it's their risk and reservations. But when you can actually give them something to use, that's where you really learn where you've made some errors in thinking and can make course corrections. So my point about this is that this kind of thing isn't, technologists always want to do the R&D, but you need to bring in other stakeholders early in the process and gather their thinking to help flesh out the user experience and this customer knowledge. And it's not the skill set just of engineers. And in fact, I'd say the engineers tend to be a little bit more around, I want to do this autonomously, and I don't really care about all these other things that aren't pointing me in that direction. So you have to have a combination of ability to stand back and really listen and not just do what you want to do. Okay, I'll close out with a few autonomy challenges. And these are not complete. In the question and answer period, we can talk about more. But this is some of the key things that I think I have big concerns about that we're working on today. This one's an interesting one because we have to build and maintain trust in automation. I want to go back to the last slide where you saw this mowing system working. In this mowing system, there were 3 baseball stadiums in 2006 that were being mowed autonomously by this concept mower. One was the Arizona Diamondbacks, one was the Durham Bulls, and the other one was Home Depot Field. And great experiments going on in all places, working with 3 different customers. And the autonomy system was basically bolting on an existing vehicle. The whole vehicle wasn't made, completely autonomous. It was testing whether this would work. And in the baseball stadium, this rear wheel on this mower, it was hydraulically driven for steering, and it actually had a hydraulic failure where it locked into place and drug a 3-inch trench that wide across the whole field. And immediately, we lost all trust of the customer. They basically, it wasn't anything really related. I mean, it could have been related to autonomy. Why didn't we sense all these things that could go wrong with the vehicle? But the reality is we thought we could manage that type of thing. And I can show you data that compares to the other 2 locations. They never lost trust. They loved the systems. Everything kind of worked out. So, if you're going to keep trust in automation, it's really important that we maintain it, but we also prepare ourselves that there's things we didn't think about. And here's another example of this, plowing has tended to be back and forth, because you had to know where you were at in the field, right? And then when things like iTech Pro came along, we had this ability to take better turns that were shorter, and you can skip a pass. But actually, an initial reaction to that is that people didn't like it. Because why didn't you just go to the next adjacent road? Well, it's because we can save you 7% of fuel and travel distance. So you have to kind of help build that trust in these types of technologies. And so I guess the point is that sometimes technology introduces the factor that causes to lose the trust. A really interesting thesis from Auburn, I believe it's Auburn. It might be, no, this might be a different university, but Daniel Quinn, exploring the efficiency of social trust in repair human automation interactions. And this goes into detail about what happens when you just have one flaw in the system and how difficult it is to recover that trust. That's going to be our problem. One of the really interesting things with autonomy is, we have precision ag. It requires existing traditional equipment that's been automated and has the operator in the seat. And we can make those machines autonomous. Of course, the OEMs would like that, and because they have machine forms that they already have history and are working with. At the other end of the spectrum, we're seeing new things being done, like cover cropping, that you could never do in a row before, but are possible today. And maybe I saw a lot of papers yesterday around phenotyping and being able to learn from that. And those are great new elements, and they have to kind of provide value on their own. But in the middle, and really I think the large opportunity with autonomy is that you can build purpose-built machine forms that are never designed to have the human on board and can achieve the task in a different way, can achieve the outcome that you desire in a different way. And I've showed various versions of these. Some are feasible. Some all of these have been demonstrated. Actually, the most unusual one is a plug-in grid tractor that carries the cable with it back to the electrical wire. This one will never happen, in my opinion, but I did see it work, and it could cover a 10-acre field effectively and not run over the cable and chew it up in the mower. Again, I think the point is that with autonomy, we have a set of tools now from precision agriculture that are going to open the door to doing a lot of things in different ways. And on the journey to autonomy, some of the speakers earlier talked about that there's a transition period. I fully expect that we should plan that for a long time. There's going to be a lot of human interaction and autonomous vehicles working together, and we need to build autonomy so that it leverages what's taken place in precision agriculture. And if you're doing research in this area, don't try to create your own path plans, or, you need it for your research, but You really want to know, how do I integrate this with the other things the farmer is using so that I can seamlessly fit into their work processes to get the job done. My next comment is some of the challenges is the autonomous tech stack. And this is just one view of this. At the bottom level, we have machines, and we control the actions of machines. And those actions are controlled either the task state or the mobility of the machine, and they create the production job outcomes. And in the middle, we have some form of controllers on the vehicle that have awareness of the machine state. This is where perception sensors come in. They have planning systems for navigation, and then they have systems for evaluating the job quality. How's it doing in performing the task? And that's where the new opportunities in AI are coming into play. I like to think about this layer as the one side of this is that we can do job performance. That's optimizing the implement or optimizing the machine. We could apply that today, even if the human's driving, you have a human operator driving the machine. With a situational awareness, we have the larger leap of providing capabilities that replace what that operator does. And all of that's through this middle layer, through the domain controller. But the top layer is the part where is really important, and this is the ecosystem integration. I talked earlier about digital has made autonomy possible. This is where we have the definition of the field terrain and the boundaries. These are where the hazards are identified, the types of crops you're planting, the management practices that the farmer wants to use. And again, this is another point that we need to pay a big attention to the fact that these are the things that really enable autonomy, is how do we leverage those existing sources of farm management information systems. I have a second comment about this space. Maybe I'll just use that on this slide instead. That's the stack. We talked about act, sense, think. Prepare and monitor, I think, is just the point that I just made, is this is where the modeling, planning, execution, and all those types of things take place. But I do have kind of a complaint to the industry and maybe a complaint to academia to think about. We have so many people rewriting the same code over and over and over again. And if you really want to accelerate this space, then learn how to innovate while collaborating with others. Because a lot of this is just creating exactly the same thing, and you need it. You need to use it, but be careful on what you're creating versus what you can leverage. And that's just a way of reducing the cost of getting into autonomy. You don't have time. I've had this problem with engineers or graduate students that they all just want to see it move based on their code. But the reality is more and more today, especially computer scientists, are putting together systems and bringing together lots of components that exist through GitHub and other resources, or using the ROS operating system. You know, take advantage of what's out there and don't recreate everything yourself. Down in the lower part of the screen is interesting from an industry perspective, is that automated machines have had electronics since about 1990. There is some controllers on machines that probably are running code that was developed in 1990, before cybersecurity, before a lot of the challenges of the modern age, before communication. And the way this kind of works on a lot of OEM machines is that you have a number of controllers, and they each are kind of purpose-built, but they talk to each other. And then when you talk about building an autonomous system, you have this ADAS, this autonomous driving automation system that you're putting on connected to that communicates to the machine to provide those high-level functions. And so you have N numbers of ECUs, or engineering control, ECUs, they're ECUs, not ECEs, and you have lots of different functions. Then if you also have the possibility that as electronics mature, if a company decides to upgrade their electronics, that you can have more domain controllers. And the difference between this is how data is shared across the machine. If I had my choice, I would like to have the one on the lower right, because that would mean that my intelligence system has all the data related to that machine without care. I mean, it can do it on the left, but it's like you're passing data packets between these different devices. And so, in industry, we need to move towards more maturity. We're always comparing whether it's a tractor and implement from the same manufacturer, but I think down underneath the hood and inside of the machine, there could be differences that you can detect and perform better, that serve customers better, if you have an understanding of the electronics architecture that you're trying to implement. Okay, again, I'm kind of revisiting this baking a cake ingredient, but this is a different version of this. This paper by Thompson is a maturity framework for autonomous solutions in manufacturing firms. And it looks at the interplay of technology, ecosystems, and business model. And if you look at the graph, they show that how there's a progression from operator-assisted, semi-autonomous to autonomous. And they've studied industries that have made this jump. Not agriculture, other industries, mining and a few others. And there's a kind of a slice of this pie that's related to the tech development. And the problem we have is that everybody believes it's the tech development that differentiates. In the ag industry, OEMs tend to be very, very centralized around their products and stuff and thinking about what they do. And so their technology development would live in that space. But what this study pointed out is that there were two more factors that were more critical to the success of autonomy. And one was how you started integrating with an ecosystem of players that provide services and capabilities that you could use in your product. So that was the second piece of that. The third one is business model. The business model for the traditional machine and the business model for autonomy are not necessarily the same. And a lot of the challenges are that people don't think through delivering it differently. We think about, well, you buy a tractor from a dealer, you deliver it, and the farmer's just going to sit there and run it autonomously, and that's it. Well, that's one business model, but it's a pretty hard one, and it requires a lot of complexity and training the dealers and things like that. So I think the point I want to make is that successful automation to autonomy is integration of these three things together, one. And two, whatever approach you take to moving away from technology towards business model and building an ecosystem of partners is going to be pretty important to reach the higher levels of autonomy. Okay, so what does the future look like? I showed the original curve with the S-curves. And there's kind of like two destinations that are possible. Autonomy doesn't just change machines, it changes how we deliver value. We imagine, it's possible to imagine worksite as a service where you pay for outcomes and not equipment. Or you share the autonomous fleets with other farmers. And some of these models are already emerging. And on the left side, it kind of shows that we could be heading towards intelligent implements with onboard monitoring that just makes it really simple for any skill level of operator to work consistently all day long. And the AI helps achieve the production goals. On the other side, we can think about having more fully autonomous systems where integrated with AI, these autonomous systems are a trusted advisor that help manage the business and work site. Okay, just take a few more minutes and then I'm going to skip over my last section. I do want to talk about safety. I've shown earlier that we have these discrete controllers that are used in automation. These are not going to be the things that provide the lower part of an intelligent controller. The upper ones were built with different design constraints, and autonomy has its own set of design constraints that are required. So autonomy also is going to introduce some new challenges, new hazards. By the way, the manufacturers are built around building machines that humans drive. And they're going to require new capabilities to have this comprehensive safety validation. What AEF is doing is excellent, but we just are early in that journey. Now, safety is also ODD dependent. What's ODD is an operational design domain, and it describes the beginning of a step that's going to be safe all the way to the end. And it could be, for example, entering a highway on an entrance ramp and exiting on an exit ramp, and you can operate anywhere on the highway. That's an ODD for automotive. Agriculture, we're going to need these as well, but some machines perform some job steps with common requirements, like tillage and planting. They kind of have similar ODDs, but different ground effects. Other machines have coordination of tasks, like unloading into a combine. And there's a wide range of field and crop conditions that can impact specific operations, so moisture, soil condition, dust, all of these types of things. And agriculture has a much harder lift than other fields. Actually, I would show you the way that we don't, this is actually an interesting slide on how we used to have to test and validate safety. So it's a little bit of an aside from the slide, but you'll notice that no one does this anymore, okay? You have a human, it's the graduate student that wrote the code, and they're standing in a row, and the system stops. There's more distance there than it looks like from the tractor cab, but there's also somebody sitting in the tractor. But we need ways of scaling and getting this learning across the complexity of agriculture that doesn't require physical testing all the time. We have to get beyond that, or we'll never cover enough conditions. And safety is unbounded. We have a lot of challenges from mixed brands of equipment, tractors and implements. A farmer buys an autonomous tractor, it's only good for tillage, but they decide they want to use it for planting, so they go beyond the intended purpose. How do we manage that? There's annual safety certifications to make sure that your sensors are calibrated and working effectively. And then there's also black box recorders. We have to record when things go bad. So the ability to look at that data and see what was a fault is an important part of future autonomy. And I'm doing a project today with horseradish producers. Another problem is agriculture is cultural. And I think if you got, many farmers farm similarly, but a lot of farmers farm uniquely. And the horseradish farmers are the biggest part of this, because when I heard about this problem, I imagined there was a group of farmers that only grew horseradish. They have big issues. They have a long season crop, 15 months. There's only 3,500 acres in the United States, and most all of it's in Illinois. And they have problems with it's a root crop, so you have to plant it by transplanting, and have weed resistance problems. And the way they solve their weed problems is down on the lower right. You have basically people with hoes. So you kind of look at that and say, well, actually we can come up with a toolbar solution so you can drive a tractor and do see and spray. There's really lots of good opportunities to help these groups. But what you kind of miss is their frustration, because they also raise corn and soybeans, and a lot of it. And they have a lot of technology. They have, equipment with see and spray and operations center and things like that. But they have a part of their business that gets no attention from the people that sell them equipment. And so it's kind of I think this is also true in other areas. Farmers are diversifying. There's some orchard growers that raise soybeans in the East Coast to kind of like keep their workforce busy. So as we go on this journey, we're going to have to understand that we have a lot to go to help the small to medium enterprises and democratize autonomy across all of agriculture, lots of different conditions. And I'm going to skip over this, and I'd like to use the last couple of minutes, and I won't talk about Gen AI now. I'm going to stop there and take a few questions. So thank you for your attention.
So we have a few minutes for questions, and I'll bring you the mic. If you have a question, just raise your hand.
Thank you very much for the presentation. It was great. Actually, my question, I'm trying to consider different things in my mind, from safety to efficiency to machines productivity. These days, there's a trend that they are going to automate machines. For instance, automating big harvesters, tractors, integrating sensors like Sabanto tractor that you showed, the small one. So we have kind of the same trend for big machines, and I'm trying to get your thoughts on it. Considering safety, machine productivity, efficiency, what do you think about next 10, 20 years? Will we have big autonomous machines, or those big, say, 300, 400 horsepower tractors will be replaced with small machines?
Yeah. This is a good question, and I think it's a little bit of an open question. My initial thoughts were that if you start thinking about protecting the print of a machine, the challenge is sensors to protect the implement. So a tractor has a body width, and we see some really T-shaped operations. But even, large sprayers, it's hard for the operator to see the end of the boom, and sometimes damages happen because of that. So we don't actually ever instrument these things with sensors until See and Spray is now putting the sensors, but they're all looking kind of close in. I think autonomy could be limited based on the form factor, and it actually impacts productivity negatively. So for example, you can have a high horsepower tractor, but if your implement can only be as wide as the back end of the tractor, or whatever you can afford to protect, then your productivity is going to not be as effective as a bigger machine with a human operator using auto track. Now, it also raises the question, do we need to measure productivity in a different way? If I can work and do something else while this is doing something at a slower productivity, it might be okay. It can work at night and I don't have to. I don't have to go and tender it. That could be an acceptable solution. Or if I have a larger system and a smaller system working together, it helps increase the productivity. It just doesn't do it in a perfect double.
I think your mic died, so.
I have seen some new ideas in sensing that, you're starting to see, a lot of people have just said, well, I can sense out to a certain range, but now you're starting to see companies have multi-range sensors. And maybe that's a way of addressing some of this problem so you can see a larger footprint. I built an auto docking system for recreational marine, and we solved it by having 360-degree vision around the whole boat. But that's kind of expensive in stereo vision, and of course, boats are kind of on the order of the cost of giant sprayers. So, did that answer your question effectively? Yeah, thank you. Yeah, well, part of it is people may not. I may not be perfectly right about this, but it's a consequence of our success in agriculture. We had 100 years of mechanical engineering innovation, and that made machines bigger and wider and more horsepower. And it turns out when you have an expensive machine like that, you could afford electronics earlier. Those machines have had electronics since the cars have had electronics, and it's made those machines more productive. But if you look at smaller vehicles, it's only in past 5 to 10 years that smaller vehicles and even mowers are starting to have ECUs that control that. And it's because companies have realized now that they can leverage that investment across their entire business. So, and as a result, things like orchards have suffered because they haven't had tractors and machine systems that have had the electronics capabilities. They've only been able to do retrofits that are kind of partial solutions. And in fact, in many cases, that's one problem. The second problem is orchard growers are, at some point, every farmer is going to be about the seed and the plant itself, and every OEM is going to have to think about closing the loop around the seed and the plant and the operation, and not just driving around the field or that type of thing. And orchards, they're way ahead of this in this space because they have not decided what row spacing there should be. So if you look at it and you want to have a business that's for a market, you see that, well, there's different architectures of tree canopies and there's different widths and they're changing. And, actually the example that I showed, I don't know if I showed this one, with a tractor driving down through orchards, the farmer said he would never let his worker drive that tractor down through there because it was too wide. It was 4 inches on either side. But he was okay with it happening autonomously because of that. So I think that is part of the complication, is that we can do it for those spaces, but the products have to create volume, and maybe this is an area for startups. I think the examples of logistics in orchard also are a great example of going after something that's important for them. You're looking at their pain points, and it's labor and keeping people in front of trees, picking apples, still try to figure out how to autonomously harvest, but focus on the logistics, which is easier to do, is a stepping stone. And they're different stepping stones.
John, I saw other hands raised. We're out of time, but I think John's going to be around, so just reach out to
corner
him
me.
directly. Excellent talk. Let's give John another round of applause.